Hello, welcome back. In this segment, I want to show you how we can use predicate logic to model a set of logical statements. For example, you see here a Scottish private club puzzle, which is having 6 rules regarding membership. We want to prove that the rules are so strict that no one can be accepted. Okay, so let's see how to model it using predicate logic. Every non-Scottish member wears red socks. So we need some way to model, okay, somebody is a Scottish or not, right? So we need a predicate, let's call it the yes, yeah, which takes a member X as input. What it means is that S of X means member X is a Scottish. Wearing a red socks, you can also model it like, for example, R of X means X wears red socks. So we can identify all these predicates by reading the rules. And then we ask the solver to figure out, can you find an X such that all of the rules can be satisfied? In this case, the expectation is that no such X can be found that will satisfy all of these 6 rules that are encoded here as a bunch of predicates. Okay, that's the high-level idea. Now let's look at Z3 specific syntax and model it in Z3. We declare a variable called member. We keep it abstract. We don't know what member is exactly, but we just keep it abstract. That's the reason for declare sort. Yes is a function to denote somebody is a Scottish or not. So member to a Boolean variable. Okay, somebody wearing red socks is a member to a Boolean variable. Wearing kilt, married, out on Sunday, all of these are modeled as a function from member to a Boolean variable. And X is a member. Okay, what is a member? Member is just a type. The rules are now encoded. Every non-Scottish member wears red socks. How do we do that? For all X, if they are not Scottish, you can see here not Scottish is encoded here, implies they wear red socks. So here is red socks, here is implies. Similarly, every member wears a kilt or doesn't wear red socks. So for all X, either they wear kilt or they don't wear red socks. Married members don't go out on Sunday. M of X for married, going out is for Z of X. A member goes out on Sunday if and only if he's a Scottish. So if and only if his model with equal to. Going out on Sunday means Scottish. Scottish means going out on Sunday. That's the reason I put equal here, double equal. Every member who wears a kilt is Scottish and married. So if you have a member who wears kilt, right, that says they have to be Scottish and married. That's the reason for this portion. Every Scottish member wears a kilt. Okay, that's we are Scottish, they wear a kilt. So I have all the 6 rules and I add it to the solver. So I create a solver here and I add all of these rules. And then I check whether they are satisfiable or not. And now we will just run the Scottish private club puzzle. And you can see here, no member of the club is the output. Let's confirm where it is coming from. It's coming from here. That means it's not satisfiable. Okay. What it means is that Z3 was not able to come up with a mapping between these functions, taking member as input and Boolean as output. There is no such X as possible. Essentially, that is the meaning of non-sat in this case. Interestingly, we can ask Z3 to give us a proof why it thinks there is no solution possible, but the proof itself is going to be somewhat lengthy. So I'm not going to read all of the details of the proof. We will go here and print proof. Okay, so the proof itself is shown, but it's rather lengthy, and I'm not going to talk about all the details of how Z3 came to the conclusion that these set of predicates that we modeled cannot be satisfied. Okay. That's basically it. Thank you very much for your attention.